Building Science 101 is sponsored by Anderson Windows and Doors, Builder's First Source, Huber Engineered Woods, Polyguard, Sashco, and ViewRail.
All right, my friends, Building Science 101, Episode 4 coming at you. Building Science, Energy Efficiency, and Environmental Responsibility.
You know, this is one of my favorites. I know we have limits as to what we can talk, but if you wanted to pull up a chair, I can go on for about 8 hours.
We won't go that long.
Talk about this, but it is, you know, it's really interesting in today's world. You kind of have a bunch of people that say, "Oh my God, climate change, this and that," and I'm not going to give any public opinion on that because that just gets me in trouble. But you have those that believe, hey, we should do this, those that believe we should do that. You know, I'm in the camp where a house is thousands of decisions.
That's right.
We should make the best decisions we possibly can for our clients.
100%.
Right. I don't care about passive house labels or any of these green building labels or platinum, silver, or whatever levels. It's tuning the project to my client's budget and working with them to get the best possible result in energy efficiency and environmental responsibility.
And my favorite word when I think about both efficiency and environmental responsibility is stewardship.
Yeah.
You know, a steward is somebody that doesn't own something but's taking care of it for someone else. And when I think of energy efficiency and environmental stewardship, or responsibility rather, I think of stewardship, right? I don't own a lot of what I get to use, so I need to treat that like a good steward would. And so as we get into this particular talk here, I think that there's going to be some interesting things you're going to find on this particular section because some of Steve and I's advice might be different than what you might think. Why don't you start off with energy efficiency, Steve?
So energy efficiency, this one's a pretty easy one for me to explain. I again call up the two-headed monster, right? The very first part of energy efficiency is I need to purchase that energy that I'm gonna translate or transform into heating or cooling, but I need to purchase it or get it at the lowest possible rate possible,
Yep.
right? So whether I'm buying gas or I'm buying electricity or I'm buying oil, if you're still up in the Northeast, I want to get that purchased energy as cheap as possible. And then I want to convert it as inexpensively as possible. And then I want to, the second stage of that two-headed monster is hold on to it as long as we possibly can.
That's right.
Now, we're here, this is episode 4, and every episode we talk about control, right? And when we talked about it initially, we said you're going to hear about it in every episode, right? We talked about building and tuning the house to the climate and the building assemblies to that climate, right? And getting that stuff straight so that we can get control. Well, it's the same with energy efficiency, right? We want to hold on to whatever heating or cooling we have as long as possible. Now, there's a couple myths there, you know, in terms of cooling. Cooling doesn't move. So in the north, where it's nice and cold, and I have my little architecty plan here, if I'm inside here, and again, I want it to be 70 degrees inside, and it is 0 degrees outside, then I have a delta across that wall of 70 degrees.
That's a big delta.
So I need to perform, that wall needs to perform exceptionally well. If I move down here in Texas, that in heating mode, the worst case is probably, this might get down to 60 or 55 degrees.
Yep.
Right? So we're talking, you know, 10 or 15 degree delta. That's not a whole lot. But in the summertime, when it's 100 degrees here in Austin, and I go inside and I want that to be 70 degrees, then I have a 30 degree delta there. So no matter how I look at it, gaining control is about creating an assembly or a building that can control that delta. Now, Obviously, heating can be a little higher only because those temperatures get drastic. But one of the myths I believe that I have seen in energy is people kind of, south of the border here, in the warmer climates, they seem to think, hey, yeah, it really doesn't matter. That's for you guys that are heating. No, you're buying electricity.
That's right.
And in some places it might be cheap, but in some places it's really expensive.
For sure.
And depending on, where you are, we have some places where you're probably upwards of, 24, 26 cents for electricity
Per kilowatt
hour. Right. And, where in some places, if we talk to our buddy Will, he's like, yeah, we probably pay 8 or 9 cents a kilowatt hour there, or up in the Northwest because a lot of their power is hydro. But holding on to it as long as possible. And remember, when it comes to heat flow, and I'll write this down because you need to see it to believe it. Heat flow moves from hot to cold.
That's right.
Cold doesn't move.
That's right.
I hear people all the time when they're going to be talking about a building, oh, well, I'm going to insulate that so the cold doesn't come in.
What?
Cold doesn't move.
No.
Cold doesn't move.
Let me throw a great example of that helps me visualize that. When I moved to Texas 15 years ago, Yeti coolers were just starting out. And I just had a cheap foam cooler in the back of my truck. I'd go to the job site. At the end of the day, my ice was all melted. But some of these guys that I was seeing with these new fancy Yeti coolers still had ice in the back of their truck. Now, ice is not an expensive item, although it has gotten more expensive the last couple of years. So I would have to buy ice every day at 7-Eleven to keep my cooler cold with that day's beverages if it was going to be 100 degrees out. That heat was flowing from more to less, from hot to cold. My cooler was getting heated up from the outside because it was hot in Texas, and it was melting the ice inside my cooler. Those Yeti coolers, we're going to come back to this as we talk about control layers in the future, but those Yeti coolers have a few things that make them better at retaining ice. And we could take that same example for our houses, for our walls for our houses. As that moisture moves and as that heat moves from more to less, we need to remember that because that high school science physics principle of heat flow and moisture flow affects our buildings. It affects how we insulate them. It affects how we're going to control both moisture and vapor drive in our buildings. And it's going to control why we want, or it's going to help drive why we want airtightness on our houses as well.
Yeah, and we're going to dispel a myth because as you were talking, you inspired me to come up with this comment. If, in fact, cold moved, the ice would never melt.
That's right.
Right? The ice, it would continue to grow ice as the cold moves.
That's a great point.
Right? But the fact that the ice melts suggests that heat is the only part of that equation that's on the move.
That's right. Great point.
So when you're down south, you're not necessarily talking about the heat that wants to leave your building, like in our 70-degree northern example, when it's 0 degrees out. All that heat is trying to get out, right? Heat, and it's not necessarily that heat moves. You have to understand heat and cold, say they're on a scale, or say it's like this, cold, really cold outside, relatively warm inside. Well, that heat is trying to equalize that cold. It's always seeking an equalized position.
That's right.
So as that heat moves across that assembly and moves to the outside, we're losing that heat. We want to hold it in. But guess what? When we reverse that order and we come down here, say in Texas, and it's 100 degrees outside, 70 degrees inside, well, now we're talking about all of this heat that wants to move across my assembly here and move from the outside inside. So Mother Nature doesn't give a damn about walls, roofs, labels, passive house, nothing. Mother Nature has a very simple rule. It moves from hot to cold, right? One of probably the best thing Joe ever instilled in me was when he would say, it's not rocket science, it's building science. right?
It's really high school physics we're talking about.
Yeah, people want to create a dissertation about heat flow, and I'm sure people have, and good for them. It's good. But for all of you out there watching this video, walk out of the room when we're done and say, oh, heat moves from hot to cold.
That's right.
It's the only movement, it's the only law that Mother Nature has in terms of that. So when you build a building now, you have to ask yourself, if I want it to be 70 degrees inside and the outside is X number of degrees, which way is the energy flowing across that assembly?
I want to point out too, Steve, as we've talked about building on this ladder, on this foundation, that we talked about comfort on the last one, but now we're talking about energy efficiency. And as we talk to people that are going to build a house with us as builders, efficiency is not the number one thing I don't think they're concerned about. They may say it, but really comfort is really much more important to people. And efficiency comes as a byproduct of comfort. So if we have less heat flow through our walls, that doesn't matter which way it is, if we have less of that, we're going to ultimately be more comfortable in our buildings because we're going to be able to gain control and then use a smaller amount of mechanical equipment to maintain that control. And once we get that flywheel going, it's easier to maintain that. Whereas if we have a very little control, very little insulation, very little ability to stop moisture, we're going to have a bigger engine to do everything. And bigger engines use more power, use more gas, right? No matter what your sources of power are in your house, you're going to use more of it. So if we can gain control and get comfort on our houses, that efficiency is going to come with it.
Yeah, and I can't help but always reference Dan's house. And the reason, so you understand why I reference Dan's house, he's a retired engineer that built his retirement home, and he's a retired mechanical engineer. So Dan has measured everything about his house. He's done all kinds of tests. He's always sending me emails saying, hey, guess what I did last night? I did this, this, and this. This was the result, right? All these people that say this would happen. No, that didn't happen. This is what happened. But when it comes to Dan's house, one of the things that I thought was really interesting was 57%. Now, his house is up on Cape Cod, up in the Northeast, right? Heating degree days for you nerdy people out there, we're probably talking somewhere around 3,000, 3,400, something like that, maybe a little higher. But 57% of his heating bill is served by sunlight, right? It's a passive house. We have nice southern orientation.
Wow, that's impressive.
So when I talk about purchased energy and getting it as inexpensively as possible, well, positioning the house just right allows for that sunlight. Now, if you did that house in Phoenix, then you might have a problem having the sun streaming in on your living room and you'd be cooking and paying for a lot of air conditioning. But in the Northeast and in the summertime, we have some issues that we can talk about later date that we solve with shading. But, we looked at climate tuning that house for that environment. And so we oriented it such that I think on the south side, we were upwards of about a 38% glazing ratio against 38% glazing against the opaque wall. On the north side, we're at like 7%.
Let me verify this because I actually don't know the answer. Is that often referred to as passive solar heating? Is that correct?
Yeah. I mean, I think this is definitely part of passive house. And passive house is the one that, they use that two-headed monster. Except rather than talk about purchased energy of buying gas and electricity, they want to capture as much free energy in terms of sunlight as possible and orienting the house. And then they want to build a really good envelope that's super tight because they understand once the energy gets through the glass, I want to hold on to it as long as I possibly can.
Yeah.
And
give us a quick primer on how the sun works in winter versus summer and how that modeling of yours for Dan's house worked out.
Yeah, so the interesting thing, and we'll talk about this later because it can get really complex, but the reality is that the sun is only in the same position twice a year, right? Every day, today at 1 o'clock, the sun is in a different position than it was yesterday at 1 o'clock. And it'll be again in a different position tomorrow at 1 o'clock. That's why our days get shorter and they get longer. June 21st, the sun is, if I use the the compass here, well, in the summertime, June 21st, the sun is down in the southern sky and it's rising, or northern, sorry, and the northeastern compass, and then it rises up and it sets on the northwestern side.
Yep.
In the wintertime, it's up here in the southeast, and it's much shorter day. Right? Now, the other thing to understand is that as that sun travels, right, it obviously comes up, if you're by the ocean, and it gets pretty steep in the summertime. Where we are, I believe our numbers are December 21st, it's at about 13 degrees in elevation. And for our summer solstice, I want to say 71 degrees. This is information you can look up, but it's somewhere in there. So you can see in the course of 6 months, basically the sun rises 57 degrees in its apex when it's due south.
So in other words, the sun is higher over the house in the summertime, and the sun tends to be lower in the wintertime. So even with some overhangs, that lower sun in the winter can penetrate those overhangs
much deeper
and can get into the house and heat it up, whereas those overhangs are providing shade as the sun is higher into the house, right?
Yeah. And another myth is, when you start talking about energy efficiency or sunlight, people say, oh, I'll just put shades on. Well, understand that if I have a window and the sun is streaming in through that window, if I put a shade on the inside of the house, the heat energy is already inside the house. So the shade is useless. It's blocking the light, but it's not blocking the heat energy that came in through that window.
That's right.
And if we shade on the outside of the building, then we're basically blocking that radiant energy.
And what are I'm sorry to interrupt.
Yeah.
Give us the quick primer on the types of energy transfer as you talk about that.
Well, we have conduction, right? And that's basically passing through materials.
Yeah. So when I touch you, if I've got a fever, you can tell that I've got a fever because I'm hotter.
Exactly.
Right? That's conduction.
Convection.
And we've all got convection ovens. The convection oven uses air movement as well as the element getting hot, and that air movement speeds up the cooking. It transfers the heat quicker by moving that air.
And of course, our favorite, the sun, radiation.
That's right. So when I'm in the sun and I feel the sun's rays on me, I heat up faster than when I'm in the shade and the sun's energy is
Radiating.
blocked. That's right. It's being stopped by that. And you're going to hear us later talking about some radiant barriers. But that shade on the outside, Steve, if I'm understanding correctly, is actually rejecting the sun's radiation rather than having those shades on the inside. The sun's already come through the window. The shade gets hot. If I were to use a thermal camera on that shade, I'd see that shade was, 100 plus degrees, even though my room was 70 degrees. And now once that shade gets hot, even though it maybe stopped the radiation from heating up the carpet, it's now radiating itself, right? Because it's turned into a bit of a radiator, and the shade itself is hot, radiating that energy back into the house.
Yeah. So, that's pretty much energy efficiency at the kind of 30,000 foot level.
Yeah, we still have more to go because we still have to get an environmental
We got to get environmental responsibility. Like, this is a can of worms that's ready to explode. But let me start by saying this. I don't know everything, but I know a couple things. Environmental responsibility. The minute I go into that field or pasture or wherever I'm building the house and I put a shovel in the ground and alter the ground, I am in debt to the construction and to the environment on that house. Nothing I am going to do about that house. I can make it 10x zero energy, and it's still not going to be a benefit as if I had never gone into that pasture and didn't build a house.
I think this is going to blow a few people's minds, Steve.
Yeah.
I mean, ultimately, any building project, a new construction project where you're getting in and building something, there's going to be a debt to the environment. You're actually using resources to do that. Some of those resources are very precious and are hard to replace. Other resources, maybe those 2x4s, are rapidly renewing and carbon sequestering and have a lot of benefit. So anytime we build something, we're actually in debt to the environment.
We're in debt to the environment, and we're trying to work our way out of that debt.
Yep.
And we're never going to get above zero,
Mm-hmm.
right? We're never going to get a credit on the environment. You can say whatever you want, sustainability, I'm building passive house, I'm doing this, I'm doing that. You're never getting above that credit line. You're always in debt. So then that raises the question of how much in debt do I want to be with the house that we're designing and building or the remodeling job that we're doing?
That's right. And I would say that in general, remodeling is less environmentally costly than building new, and not moving into a finished house that's completed is ultimately probably the best thing, because that environmental debt was already paid decades or maybe even centuries ago.
Yeah, I'm always discouraged when I drive by and I'll see somebody putting up a new house out in a field or cutting down, a half acre of trees, and they're building a new house, and they're building what I would consider a garbage house. Now, I know they're going to say, well, we're building the code and we're doing this. But the reality is you have thousands of choices, and there's probably at least 100 choices that I could help you make that are right off the top, that wouldn't add any cost, but would make a world of difference in that house, and also help your clients gain control.
Yep.
They gain control, they gain comfort, they gain health, they gain energy efficiency. All of those things, and durability, all of those things help with the environmental responsibility, right? If you take durability and we put durability up against environmental responsibility, and this is not me, this is Joe talking, because he told me this one day. We were sitting down, and he said, if I build a house and it lasts 50 years, right, and then they tear it down and build another house. Well, if the neighbor builds a house 100 years, then they've have the resource accountability of that house.
That's right.
Next to their neighbors that only lasted 50 years.
For sure.
Right? So, in context, when you're thinking about environmental responsibility, and I label it as it's a moral choice, right? It's not something, there's nowhere in the code book it's going to say, you can't use this, you should only use this information, this, unless it's a life safety issue.
Yep.
But moral choices are not in the code book. Building inspector doesn't give a damn about your moral choices and carbon counting and carbon footprint. He doesn't care. It's a moral choice. So that in those thousands of decisions, we want to try and make the best decisions. Now, as an architect, it becomes somewhat of a juggling act, because I can sit here and say, yeah, this is probably a slightly better moral decision, but this one is talking about durability.
Mm-hmm.
And for me personally, I live by, if it don't last, it don't matter.
That's right.
In the durability.
Love that.
So I want to make a building that lasts, that has the right choices. Because if I do that, then we go back to Joe's little explanation about having the resources.
The other thing I want to bring up on this point, and I don't want to necessarily say that other cultures are better than our culture, but you and I grew up in America, a fairly young country in the scheme of the world's countries. Where I grew up in the Northeast, I really didn't know any houses that were older than maybe 150, 200 years old. Where I'm in Texas, there's very few houses here that are older than 100 years old. Right. Whereas when Steve and I have traveled through Europe, and we're not saying Europe's the best and we should build like Europe. Mm-hmm. But one thing that's different is when you grow up in a culture that has buildings regularly that are a few hundred years old, or maybe even when I visited Japan, I was in some buildings that were 1,000 years old. I was in England a couple years ago and stayed in a tavern that was built in like the 1200s. It gives you a different perspective on longevity. And I think one thing that I'm hopeful that you guys will get from this series is that it's not hard, it's just a little different, and making a few more choices, and we can build a building that, instead of what you mentioned earlier, that might last 50 years without a problem, that might actually go several hundred years without a problem. And what a different environmental responsibility and a different environmental footprint a building that's built to last several hundred years than maybe a building that you're going to be thankful to get out of the first mortgage without having some problems or having major issues or major things that need changed or replaced on that house. It kind of goes back to a little bit of an old story I tell clients about hardwood floors. I'm a big fan of white oak floors. In the years I've been remodeling, I've pulled a lot of white oak floors up, de-nailed them, saved them in the corner, put them back down, sanded them and finished them. And that 100-year-old floor looked brand new again. And white oak is a very slow growing tree. This is a precious commodity. Maybe it got cut down 10 years ago, last week, or 100 years ago. I think white oak floors are a really sustainable, a really good environmental choice for a floor because they're so darned durable and easily able to be reused. Compare that, let's say, with a luxury vinyl floor that looks amazing and actually looks a lot like wood the day you put it down, but 10 years from now, it needs to be thrown in a landfill. And you got to build a whole nother floor in that house. It can't be resanded. It can't be refinished. It simply gets trashed. The same is true with carpet. I've really tried to avoid carpet on my houses over the last couple of years because it holds things that your feet bring in, and then as you step on it, those get released into the air. And invariably, within a few short years, it looks bad. You have to throw it away and get a whole nother set of carpet in that house. So I realize these are costly choices, but sometimes the more costly choice, the more thoughtful choice, the choice to build a smaller and better built house is the better choice ultimately for you, for your grandchildren, and for the environment that we live in.
Yeah, you bring up a really good point because I'd just use your example of hardwood floor against luxury vinyl tile, right? One of the things when it comes to the environment is this term embodied energy.
Yeah.
Right? So you take the luxury vinyl tile, well, somewhere in the world, we're extracting a bunch of chemicals.
Yep.
Probably a lot of them are petroleum-based.
Yep.
They're being trucked or trained or shipped to a certain location. They're going to get refined in a certain manner. Then they're going to get trucked or shipped again to the manufacturing plant.
Which may be halfway or all the way around the world.
Across halfway around the world. And then that stuff is going to get put on a truck, a train, or a ship and get shipped out somewhere.
That's right.
As opposed to the white oak, that might be getting milled 200 miles from your house in a sawmill, and then it gets delivered via a truck or through the distribution channels and comes, but the embodied energy might be a lot less. The embodied energy is basically all of that cumulative effort to extract it to the time that it arrives on the job site and gets put in, right? If something is a lot more complex, or you have to take that vinyl flooring and now I have to buy some type of adhesive that got extracted somewhere and mixed and then put down on the floor and mixed to be put in to get that vinyl floor, as opposed to a nail that goes in my oak floor. There's all of these things. And again, I'm not trying to judge you. I'm just trying to expand your spectrum of thinking that, hey, when you go to your local lumberyard or resource center, you might want to just start asking just a couple questions. Hey, do you know where that's manufactured? Or do you know what that's made out of?
Yeah.
Do a little bit of research, because there might be an alternative that raises your credit score, right? And it gets you a little bit more out of debt.
Man, we went through a lot, Steve. Really, really good stuff. We talked about energy efficiency. We talked about environmental responsibility, which I think ultimately is being a good steward of the resources that you've been given, whether that resource is the clean air in your city, the clean water in your rivers, or this earth that we get to steward for some 70 or 80 years, maybe, if I get to live that long. My hope, guys, is that we've encouraged you guys to build better, to also think about building, frankly, and whether you need to build, because any building project is going to have some debt to the environment. Anything you want to?
Yeah, I just want to leave you with one thought. The next time, if you're a builder, architect, homeowner, before you go out and start bragging about how great your house is, if you really want to brag, start talking to me about how you minimalized how bad you were when you were building that house.
That's a great point.
This episode of Build Science 101 brought to you by our friends at Sashco. Now, if you're not familiar with this company, this is the maker of Big Stretch, of Lexel, of Slab, of Through the Roof. They've got a whole suite of high-performance products that we use all over our projects. How did you come across these guys,
so
Steve?
as an architect, dealing with details and bringing them down to the finest details, especially when you're doing high performance passive homes. You know, the smallest of cracks add up to become very large air leakage numbers. And here we are talking about performance in our 101 series. And, you know, Sashco is the one that bridges all of those little gaps, and they have a full spectrum of material so that whether it's a crack in a slab or a crack in a wall or a need for sealant there, you know, they have their concrete products, their roof products. It's a one-stop shopping.
Yeah. Here's my quick story from Sashco. In my previous life, before I started my custom building company about 20 years ago, I was a warranty manager for a production builder, and we used really, you know, kind of inexpensive products, whatever was available, whatever the painter wanted to pick up. And I found that when I came back to that 1-year warranty call on my houses, every house had $800 or so worth of recaulking, repainting, drywall, all that kind of stuff. And I just assumed at that stage in my life that everybody's stair stringer, everybody's crown mold, everybody's base molding was going to crack after being in the house for a year. We just kind of budgeted it in. As I started my home building company, I did a bunch of research and said, there's gotta be a better product out there. Like, if I spend another $2 more or whatever on a product, in particular Big Stretch is what I ran into, would it perform for me? Would I not have those callbacks? And you know what? Here we are almost 20 years later. I haven't used anything but Big Stretch on my houses for all of my interior painting and caulking needs. But beyond that, they also make Lexel. Talk to me about Lexel.
We use Lexel, I mean, pretty much exclusively on all of our air leakage systems. You know, mud sill, I have my little detail where we put 2 beads of it down, sandwiching the mud sill sealer, the sill sealer there, under there, and we've never had a house. I mean, when you deal with a detail like that, you have to put a material in. We don't get a second chance at it.
That's right.
Right, so we have to put something in there that we're gonna trust and believe in. And, you know, Lexel is that.
And, you know, these guys, their motto is small details lead to big performance. That fits right in with this Build Science 101 series. You know, I've heard you say, Steve, that there's miles of cracks in our houses, and that leads up to poor blow door performance, to ingress of pests and all kinds of things. Whereas if you really buy good sealants, good caulkings from Sashco, you're gonna lead to better performance in your house. So guys, big thanks to Sashco for sponsoring. You can learn more at sashco.com.
Steve, good stuff. Guys, stay tuned for episode 5 of Building Science 101. We'll see you next time on The Build Show.